is quite different depending on the context. In the quantum mechanics or particle physics context, it may very well be allowed. In the classical context, it may very well be disallowed, or they might say that there is not a good geometry for it, okay? So keep in mind and keep an open mind to these types of things. But as far as do wormholes exist in the universe? Well, I guess we don't know. Black holes provide another compelling example in which the fabric of space is stretched to its limits. So this is the other topic that we've also spent quite a bit of time on. So black holes, remember, are another example of a physical object, of a topic that both has a classical theory and a quantum theory. So in classical theory, a black hole is a singularity. It is actually something that was predicted and totally, given to us by Einstein's equations, by general relativity, but it was considered to be a bizarre enough type of object where people were not expecting it to be real. They didn't think that we would actually find black holes or dark stars, or what they called them, dark stars or point stars or black holes, meaning that it's a singularity. It's a point of such infinite gravitational field density that even light cannot escape, right? Even the gravitational field of this thing is so high that it bends space-time in such a way that even light cannot escape. So, and in fact, that is how you set the equations of the black hole, and you find at what radius does the object become a black hole by setting it equal to the speed of light to be the escape velocity from this object. And that's how you find the radius at which this massive object becomes a black hole, and it's called the Schwarzschild radius. So this is all stuff that we have kind of covered as well. So we've talked about black holes at length as well, especially because of course, Stephen Hawking worked on them. So that's the classical theory of black holes. People were, quite, how should I say it? Quite shocked when black holes turned out to be very real. They are actually a part of nature. Black holes are a thing. Sometimes massive stars basically compress down or contract down or collapse down to a black hole when they die. If they're a massive enough star, it can very well happen. So that's a way in which we can get a black hole. So it's another example where classical theory and quantum theory will not totally agree, though, right? So this is the classical approach. Then there is the quantum approach, which actually ends up giving black holes a temperature. Point stars. Oh my gosh, point stars. P-O-I-N, a star that's a point light, a star that is a point. We're talking about astronomy, if that helps. So that's the classical theory of black holes. And in the quantum theory, it's much more of a diverse theory, in where you can actually sometimes have things escaping a black hole, depending on sort of what's happening. But with quantum fluctuations, we actually see that particles can sometimes escape black holes, and that actually contributes to black hole radiation. That actually gives black holes a temperature. So anyway, all of that was to say that wormholes may be a thing. Remember that the ripping of space-time is not really allowed in classical theory, but it may be a thing that could happen, maybe. Just like black holes had a classical theory, but then it was shown with more of a quantum approach that black holes may have a temperature. So, it's basically two types of approaches may give you a better, more whole picture, more complete picture of something, okay? Black holes provide another compelling example in which the fabric of space is stretched to its limits. We saw that the enormous gravitational field of a black hole results in such extreme curvature that the fabric of space appears to be pinched or punctured at the black hole's center. Unlike in the case of wormholes, there is strong experimental evidence supporting the existence of black holes. So the question of what really happens at their central point is one of science, not speculation. Once again, the